Hello, everyone, and welcome back to another AP Chemistry virtual lesson. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School, Go Patriots, and I am in Charlottesville, Virginia. Thank you for this particular lesson and coming back, and we're going to be continuing our exploration of Unit 2, which is molecular and ionic compound structure and properties. So we'll talk more about bonding today. I want to remind you that you can go to apcentral.collegeboard.org to get more information about how the College Board is supporting schools that may be closed right now. And again, any updates that you're looking for about the AP exam can be found at that website. All right, because we're talking about bonding and valence electrons, make sure you have scratch paper, something to write with, and definitely a periodic table. Feel free to pause the video at any time if you need to either take a break or finish a problem or get some more resources to help you understand what's going on. Let me give you a lesson overview. We'll be talking today about Unit 2 and focusing on topics 2.5, Lewis diagrams, so Lewis electron dot diagrams, 2.6, resonance and formal charge, and 2.7, valence shell electron pair repulsion theory and bond hybridization. The science practices that go along with these topics include represent chemical substances or phenomena with appropriate diagrams or models, and support a claim with evidence from representations or models at the particulate level. So today we'll talk about the Lewis electron dot diagrams, how to draw them. We'll talk about resonance structures and formal charge. We'll talk about valence shell electron pair repulsion theory and molecular geometry, bond angles, hybridization of valence orbitals, and a little bit about sigma and pi bonds. For our warm-up problem today, this would be the free response question that I had presented in yesterday's lesson. So part 1 was answer the following questions about nitrogen and oxygen. Part A, write the Lewis electron dot structure for the diatomic molecules nitrogen N2 and oxygen O2. Now, we did not look at that yesterday in terms of a skill for how to write Lewis electron dot structure. So on your periodic table, most of you should know that the valence electrons can be found for a given element by looking at the groups. Ignoring the transition metals between scandium and zinc, the number of valence electrons goes from 1 to 8. So since we have nitrogen, which has 5 valence electrons, and it's a diatomic molecule, that would be 10 electrons, the valence electrons for N2. And then for oxygen, it would be 6 times 2, which is 12. So these are the electrons we have to work with. Let's start drawing the Lewis electron dot structure for nitrogen first. So initially, we'll just connect the atoms with a bond. Now, right there, that is 2 electrons, okay? So that would be a bonding pair of electrons. I can also add a lone pair of electrons or a non-bonding pair of electrons. And I have to remember what my count is. So I have to go to 10. So we'll continue. That would be 4 right now. So 6, 8, 10. And then that's it. I have no more electrons I can add. You may remember learning about something called the Octet rule. So if I draw a big circle around this nitrogen atom, inside that circle are 6 valence electrons. If I make a double bond, well, that would now change to 8. But on the other side, this nitrogen still only has access to 6 electrons. So we're going to go ahead and make a triple bond. So that now is the Lewis electron dot structure for nitrogen. Moving on to the Lewis electron structure for oxygen, we now have 12 electrons to work with, 2, 4, 6, 8, 10, 12. And that's it. We have no more electrons, so we'll go ahead and move a pair of electrons from the oxygen on the left and make a double bond. Now that you know we have a triple bond for nitrogen and a double bond for oxygen, this will help us answer part B of this question. The potential energy as a function of internuclear distance for the diatomic molecules N2 and O2 is shown in the graph above. Based on the data in the graph and the Lewis structures that you drew in part A, which curve, 1 or 2, is the better representation of the N2 molecule? Justify your answer in terms of the principles of chemical bonding and bond energy. So as you can see on the diagram, curve 1 has what I might call a deeper valley in terms of that local minimum in potential energy than curve 2. So the deeper valley, or the lower the potential energy minimum is, that represents a more stable arrangement of atoms. It also represents a higher bond energy. And I think we did talk about in yesterday's lesson that a triple bond is going to be stronger than a double bond. So therefore, since we have a higher bond order in nitrogen, and that's going to have a greater amount of energy required to break the bond, curve 1 is a better representation of the N2 because it represents the diagram with a higher bond energy. All right, we had another problem from yesterday for homework, and this had to do with magnesium and strontium. Part A, write the complete ground state electron configuration for the ions magnesium 2+ and strontium 2+. So again, on your periodic table, you can find magnesium. And if you were to write the electron configuration of magnesium, it might look something like this. So 1s2, that takes care of helium. 2s2, now we're up to beryllium. 2p6, that gets us to neon. And then finally, 3s2. Now that would be the electron configuration of magnesium, the atom. But since we are talking about magnesium with a 2+ charge, then you would not include the 3s. So your electron configuration would look something like this. For magnesium, 1s2, 2s2, 2p6, and then you would stop right there. That's exactly how many electrons the magnesium 2+ ion has. Now for strontium, we have a lot more electrons. So if I write the entire electron configuration all the way through 5s2, that would be for strontium, the atom. If we take away these electrons for the 5s, having lost 2, then you would stop at 4p6, essentially having the same electron configuration as the noble gas krypton. And you certainly could abbreviate. You could replace all of this portion of the electron configuration up through 3p6 with the argon as a noble gas abbreviation. Okay, part B. Do you predict that the ionic radius of strontium is larger or smaller in size than the ionic radius of magnesium? Well, hopefully you can realize that the strontium should be larger, and there's a variety of reasons you can figure that out, but here are some examples of wrong answers or incorrect answers that a student might say. They know that strontium is larger. Justify your answer in terms of atomic structure and the electron configuration of each ion. So if your answer says, oh, well, strontium 2+ is larger because it has more electrons. That's not good enough. That's not specific enough. That's just way too general. So try again. You might say, oh, it's because it has more energy levels, or it has more shells. Again, you're starting to talk about electron configuration, but that's still not specific enough. Simply saying that it has more energy levels, it's not specific enough. So let's say if you said something about it has more occupied energy levels. Well, now you're getting closer. I still would like you in your answer to talk about the energy level, the difference between level 2 and level 4. So I'm going to go ahead and give you my official answer. Certainly, this is just, me encouraging you all to write good answers to free response questions. And hopefully no one out there would be satisfied with an answer such as, well, strontium is located further down the column on the periodic table. So because strontium is below magnesium and size increases as you go down, you cannot justify with a trend. You cannot just simply say size increases as you go down the periodic table. That's not giving us an understanding of the atomic structure and the reason why. So the strontium 2+ ion is larger in size than the magnesium 2+ ion. Why? Because it has additional occupied energy levels. And I go on to say that the valence electrons in the 4th energy level should be farther away from the nucleus than the valence electrons in the 2nd energy level. So that answer is clear representing an understanding of atomic principles. So be careful when you write your answers. More electrons or more energy levels would not be a sufficient answer to this question. All right, we had a part C. We're talking about comparing the lattice energy of magnesium chloride with the lattice energy of strontium chloride. Now, Coulomb's law has to do with both charge and distance. It looks like, based on the information from the periodic table, that both magnesium and strontium should have the same charge. And obviously, chloride has the same charge. So your answer should be in terms of distance. It's not going to have to do with charge, but rather distance. So here's what I said. Coulomb's law states that the force of attraction between cation and anion is inversely proportional to the square of the distance between them. I'm just kind of stating Coulomb's law in words. Now, since the distance between magnesium and chlorine, because magnesium is a smaller ion, you've already addressed that in part B, that's a shorter distance between the ions, the attractive forces in magnesium chloride should be stronger. Now, be careful that you don't omit this last sentence. Okay, you have to read the question carefully. So some students do a great job of explaining why, and then they forget to actually answer the question. They were looking for less than or greater than. So make sure that when you're reading the question, you address the question that is being asked. If a student forgot to actually say that the lattice energy of strontium chloride should be less than, we can't give them credit for what is probably in their head, but they just didn't actually put it on paper. All we have to go with as readers is what the words are on the page. So make sure you are reading the question carefully and answering the question that was asked. Okay, let's get to our lesson for today, starting with Lewis electron dot diagrams. So I'll remind you of your valence electrons once again. I'm sure you already know all of this, but I'm just going to go ahead and present this, and we're going to start with some simple molecules. Now, carbon has 4 valence electrons, and each hydrogen has 1. So we have a total of 8 valence electrons for methane, CH4. Let's go ahead and connect all the hydrogens with the carbon. Remember that we have bonding electrons as well as non-bonding electrons. So here, this would represent a bonding pair of electrons. Well, since we have 4 dashes, 4 times 2 is 8, we're done. That's the molecule. There's nothing else to write. The octet rule talks about the idea that atoms tend to gain, lose, or in this case, talking about covalent bonding, share electrons, so each atom has a full valence shell. Usually that's 8, but for something like hydrogen, that would be 2. So hydrogen only needs 1 single bond to satisfy a full valence shell. All right, this is nitrogen bonded to 3 hydrogens. This is the ammonia molecule. Since 5 plus 3 is 8, I haven't finished the structure yet, but I've just simply shown the connectivity between the atoms. That would represent 6 valence electrons because I have 3 bonds. So now we have a non-bonding pair of electrons, which satisfies the octet rule for nitrogen. So you can add both bonding and non-bonding pairs of electrons, and I would recommend you start out with single bonds, and eventually we'll talk about double bonds and triple bonds. Okay, this is water. 6 plus 2 is 8. You might say, I thought the water molecule has a bent geometry. We will talk about molecular geometry today, but right now in these Lewis electron dot diagrams, I am not worried at all about making these structures to match the bond angles or to make them look like the molecule in 3 dimensions. So this is a fine Lewis structure for the water molecule, and the octet rule has been satisfied for oxygen. All right, here we have CH2Cl2. Okay, so dichloromethane. So carbon is 4. Each hydrogen is 1, and we have 2 of them. Each chlorine is 7, and we have 2 of them. So a grand total of 20 valence electrons. So we'll go ahead and fill in the connectivity between the atoms, and carbon tends to form 4 bonds normally. So now we still have 20 minus 8. We still have 12 valence electrons we have to put somewhere. Hydrogen does not need lone pairs of electrons. It's already satisfied with a full shell, but we'll go ahead and finish off the molecule with 6 lone pairs of electrons, and now every atom has a complete valence shell. Sometimes you can have to draw the Lewis electron dot diagram for a molecule. Other times it's for a polyatomic ion like ammonium. So while nitrogen has 5 valence electrons and each hydrogen has 1 valence electron, 5 plus 4 is 9. But remember, the plus charge means that we lost an electron for this total, so it's actually 8 valence electrons. We typically, in Lewis electron dot diagrams, like to show an overall charge by wrapping brackets around the structure and then putting the charge, the overall charge, on the outside like that. Nothing else to add, 8 valence electrons, full shell. This is the hydroxide ion, which would be in this case 6 for for oxygen, 1 for hydrogen, and then because when you have a negative charge, that means you have gained an electron. We actually have 8 total. I'll go ahead and add my last 3 sets of lone pairs of electrons around the oxygen to complete the octet. All right, I mentioned we could talk about single and double and triple bonds. Let's take a look at that on these examples here. So carbon has 4. We have 2 carbons, that's 8 electrons for the 2 carbons, plus 6 for the hydrogens. That brings a grand total of 14 valence electrons for C2H6. Now for C2H4, we have 2 fewer hydrogens. That would be only 12 valence electrons. And for C2H2, again, taking away 2 hydrogens, now we have only 10 valence electrons. Let's start with a skeleton structure that connects the carbons and the hydrogens, and carbon tends to form 4 bonds. Let's put carbon in the middle. And so now we have 2, 4, 6, 8, 10, 12, 14 electrons in bonding pairs. Nothing else to add. That molecule is done. But for C2H4, after I've made the connectivity between the carbons and the hydrogens, and I've chosen to give each carbon 2 connections to hydrogens, 2, 4, 6, 8, 10, I still have 1 more pair of electrons, but I'm not able to satisfy the octet for each carbon with only a lone pair of electrons on 1 carbon. It's not going to work. So I'm going to have to take that pair of electrons and put it in a place where both carbons can have access to that pair of electrons at the same time, and we make a double bond. In a similar way, we're going to make a multiple bond between the carbons with C2H2. So I now have 6 electrons I've used up so far in drawing these 3 bonds, 8, 10, and now I'm done. I have no more electrons I can add. This carbon only has access to 4 electrons. So I'm going to have to find a way to move the electrons. This would not be satisfactory because each carbon only has access to 6 valence electrons. So I'm going to have to put the electrons in a place where both carbons can have access to a full set. So I'm getting closer, but this would be my final answer for that structure. So sometimes you have to make multiple bonds. Now don't go crazy with these multiple bonds. So for example, if you had something like, let's say carbon tetrafluoride. Okay, so carbon tetrafluoride is carbon with 4 fluorines. Don't start getting crazy with all of your double bonds. Only make double bonds if you absolutely need to do that. So try to satisfy the octet rule first, and then possibly make multiple bonds if you start to run out of electrons. All right, this next molecule we're going to take a look at, this is called phosgene. This is CCl2O. It has a total of 4 for carbon, 7 for chlorine, and we have 2 of them, that's 14, and 6 for oxygen. So a grand total of 24 valence electrons. I'm going to go ahead and just make a skeleton structure. And in this skeleton structure, I'm going to go ahead and put the carbon in the middle. And I'm going to finish off the molecule with lone pairs of electrons. At some point, I'm going to get to 24, and I think I have finally arrived at 24. So I have 24 electrons. However, the carbon does not have a full octet. Now, this is a little bit of a dilemma because I could make a double bond between the carbon and the oxygen, or I could make a double bond between the carbon and the chlorine. And for some of you all that might be thinking, why did I put the carbon in the middle? You might be thinking, maybe I'll put the chlorine in the middle. And you realize that now when you go down that road, every one of those Lewis structures, except for the structure here that doesn't have a full octet. Okay, so that one. But every other structure that's on the screen here actually has a full octet for all the atoms. So you might wonder, how do we decide how to draw these Lewis electron dot structures? And could there be more than one possible structure that would be considered correct? Well, there's several answers to that question. Let's address one of the possible answers, and that is sometimes the AP exam helps you out. So they might give you a skeleton structure. Here's an example from 2018. Complete the Lewis electron dot diagram for the HNO2 molecule. Include any lone pairs of electrons. Now, all you have to do is finish the skeleton. Or from 2017, in the box below, complete the Lewis electron dot diagram for the S2Cl2 molecule by drawing in all of the electron pairs. So they've taken some of the work out for you. Here's another example from 2015, where they have given you a structure on the left, and they asked you to complete the Lewis electron dot diagram for the structure on the right by drawing in all of the electron pairs. But in terms of, is there more than one possible Lewis electron dot structure? And the answer is yes, sometimes there is. This has to do with a topic called resonance structures. So if there is more than one equivalent Lewis structure, let's talk about that. This is called ozone, O3, which is going to be 3 times 6 for oxygen. So we have 18 valence electrons. I'll start with a simple skeleton. I will then continue to add lone pairs of electrons. So right now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, and that's it. I have no more electrons I can add. So could I make a double bond on the left? Yes. Could I have made a double bond on the right? Yes. In fact, each of these is considered an equivalent resonance structure. Now I want to caution you that you might be confused a little bit by this arrow right here. This is just a convention that we use in chemistry to indicate resonance structures, but this is not an equilibrium. So we are not saying that the ozone molecule rapidly vibrates back and forth between these two structures. Essentially, what it comes down to is this. You have two structures. Which of these resonance structures accurately describes the bonding situation in ozone? Technically, neither one of these structures is correct, but it's the best we can do. So we can't actually do this, do not do this on the AP chemistry exam. Okay, you have to show a valid Lewis electron dot diagram. Do not show half a bond or something that indicates that you haven't quite completed your Lewis electron dot structure. So the structures at the top of the screen here represent the best we can do with our Lewis structures. Technically, the true structure of the molecule is an average of these two structures. What I'm showing you here is a table that has to do with bond length. Now, the OO bonds, the oxygen-oxygen bonds in ozone have the exact same length. We do not have a short bond and a long bond. And because they are the same length, in this case, 128 picometers, take a look at a single bond and a double bond. You would not be surprised to discover that a double bond is shorter than a single bond. But in fact, the OO bond in ozone is somewhere in between in terms of length, a single and a double. So it is shorter than a single bond, but it is longer than a double bond. So we can describe the bond order of the bonding in ozone as 1.5 bonds as the average of these two structures. But again, on the AP exam, do not draw half a bond. Here's another example of a polyatomic ion as opposed to a molecule that exhibits resonance. Now, if we do the math, for carbon, that would be 4 valence electrons. And then for oxygen, that would be 6. We have 3 of them, so 6 times 3 is 18. Plus, we get to add 2 more electrons for the negative charge on the carbonate ion. That brings our grand total to 24 valence electrons. I'm going to go ahead and draw a skeleton structure, including the overall charge. And I'm going to finish all of the lone pairs. And once I get to 24, I have to stop. Well, now to complete this Lewis electron dot structure so I can have a full octet for the carbon, I have to make a double bond somewhere. I could make a double bond here, or here, or here. So in fact, we have 3 equivalent resonance structures for the carbonate ion. The actual bonding in the carbonate ion is in fact all 3 bonds are the same length. And as you can see here, that bond length in carbonate is somewhere in between a single and a double bond. So based on these 3 resonance structures, we could describe the bond order of carbon, oxygen in carbonate as about 1 1/3. It's the average of these 3 structures. Okay, well, I mentioned that we have more than one way to write a Lewis structure, but now I want to talk about which one is preferred. And this brings up a concept known as formal charge. So here's how we define formal charge. Start with the number of valence electrons that the atom normally has. You get that off the periodic table. Take a look at the atom specifically in a particular Lewis structure and count the number of non-bonding electrons that are on that particular atom. So you would subtract that number and then count how many bonds are directly attached to that atom. So in the case of a single bond, that would be 1. In the case of a double bond, that would be 2, and a triple is 3. So I'm going to go ahead and highlight the chlorine in this Lewis structure on the left. Chlorine normally has 7 valence electrons. Right now, there are 6 non-bonding electrons on that atom, and there's 1 bond. So chlorine, by this math, has a formal charge of 0. We'll continue analyzing the formal charge of the atoms to make a decision about which structure we think is more preferred. So I'm going to move on to the oxygen now. Oxygen has 6 valence electrons. There are 4 dots or bonding electrons on that oxygen, and there are 2 bonds. Oxygen also has a formal charge of 0. Let's take a look at the carbon. Carbon has 4 valence electrons. There are no dots, there are no non-bonding electrons, but it has 4 bonds. So in that particular molecule on the left, each atom had a formal charge of 0. Let's move on to the molecule on the right. And we'll look at this chlorine. So that's 7 valence electrons, 4 non-bonding, 2 bonds. So that chlorine has a formal charge of +1. Now move on to the oxygen in the same molecule. 6 for oxygen, valence electrons, 6 non-bonding electrons plus 1 bond. That would mean a formal charge of -1. So when you analyze these 2 Lewis electron dot structures, now that you know that formal charge can be used to analyze the structure, let me give you some guidelines. First of all, remember that formal charge is a bookkeeping system that will help us analyze Lewis structures. It's useful when comparing 2 different Lewis structures, each of which obeys the octet rule. So if I have a choice between the structure on the left and the structure on the right, if I have to decide which one is more preferred, I'm going to go with the structure on the left, trying to get formal charges of 0 and still obeying the octet rule. That's what I'm focusing on right now. So if I show you this screen, and it certainly needs to be a good time to perhaps pause or take a screenshot, you can then remind yourself of the formal charge and how you would go through each of these molecules and analyze them and decide that, yes, the structure in the top left corner would be the best, but all these other structures that you might draw, what makes them less preferred is that they have formal charges other than 0. In general, the higher the magnitude of the formal charge, the less likely it contributes to the overall structure of the molecule. All right, here's some other guidelines. I said it was a bookkeeping system, so it's not a real charge. If you have a molecule in which each atom obeys the octet rule, the most preferred structure is the one in which each atom has a formal charge of 0. Of course, if you have a polyatomic ion, like for example, I had given you hydroxide before. So hydroxide has a formal charge, has an overall charge of -1. So it has a hydrogen, which has a formal charge of 0 because that would be 1 - 1. And the oxygen has a formal charge of -1. That would be 6 - 7. So if you have a polyatomic ion, the sum of all the formal charges in the Lewis structure will equal the overall charge on the ion itself. Now, sometimes it's not possible for each atom to have a formal charge of 0. If you have to choose between 2 different structures, and one of them, let's say, has a negative charge on a particular atom, and then the other structure has a negative charge on a different atom, you should go with trying to put the negative formal charge, if there is one, on the atom with the highest electronegativity value. Now, I mentioned this because this will definitely come up in your homework problem. So remember the advice about putting the negative formal charge on the atom with the higher electronegativity value that will show up later in your homework. All right, next thing I want to talk about is exceptions to the octet rule. Here we have boron, which has 3 valence electrons, and of course each fluorine having 7. 3 times 7 is 21, so we have a grand total of 24 valence electrons. If I draw a skeleton structure for boron and I fill in all of the lone pairs of electrons around the fluorine, I now get to 24. You might be thinking, like you saw with the example of carbonate, we should go ahead and make a double bond between the boron and one of the fluorines, and that there are 3 possible resonance structures. Well, let me go ahead and bring up formal charge one more time. Focus on this fluorine for just a moment. We have 7 valence electrons for fluorine. There are currently 4 dots, so 4 non-bonding electrons and 2 bonds. That will give you the following formal charge. So think about that. Let's go ahead and do boron. So we have a positive 1 on the fluorine. Boron would be 3 valence electrons. It currently has no dots around it, so no non-bonding electrons, and 4 bonds. So -1. As you consider electronegativity, fluorine is the most electronegative atom on the entire periodic table. So does this structure, in your opinion, if fluorine is electronegative and pulls electron density toward itself, does this structure represent a probable or a likely Lewis structure? And the answer is no. So the dominant Lewis structure is actually the one that does not obey the octet rule, because these structures, because of their unfavorable formal charges, are less important and do not contribute significantly to the bonding picture. So it's okay for this particular example with boron for it to be less than an octet. You might be thinking, what about more than an octet? Absolutely. So here we have phosphorus pentafluoride and sulfur hexafluoride. So for phosphorus, that would be 5. For fluorine, that would be 7, but we have 5 of them. So 5 times 7 is 35, plus 5 is 40. Sulfur, we have 6 for sulfur, and we have 6 times 7 for the fluorine. That would be 42 plus 6, or 48. So how would you draw the Lewis electron dot structure for an atom where it actually has more than an octet? Well, as we talk more about valence shell electron pair repulsion theory, we'll definitely see examples of molecules like these. But be aware that there are some atoms that are what are called hypervalent. So on the periodic table, focusing on phosphorus, sulfur, chlorine, those are in period 3. And elements in periods 3, 4, and 5 can be a central atom in a molecule that is hypervalent. So because the central atom has a larger size, it can accommodate extra electron pairs. So look above phosphorus. Okay, we have nitrogen. So does nitrogen pentafluoride exist? Or above sulfur, we have oxygen. Does oxygen hexafluoride exist? And the answer is no. And the reason why is because those atoms are too small to accommodate the extra electron pairs. So now that you know that some atoms can break the octet rule, I want to talk about how this plays a role in your decisions with respect to drawing Lewis electron dot structures. Okay, so we have an example of a polyatomic ion here. Sulfur is 6 and oxygen is 6. We have 6 plus 24, that would be 30, but we also get to add 2 more electrons for the negative charge, so this would be 32. I'll go ahead and set up a skeleton structure and fill in the dots and stop when I get to 32. If you do formal charge for all of these oxygens, it would be 6 minus 7. so -1. And if you do formal charge for sulfur, it would be 6 minus 4, so +2. Well, we just were told that elements in periods 3, 4, and 5 can expand their octet, so sulfur could expand the octet. So now we have 6 bonds to sulfur, formal charge of 0. So for these alternate structures, it might seem that now you're on a new mission to draw structures with all kinds of expanded octets, and your goal is to now minimize formal charge wherever possible. Let me give you some helpful advice on this. If you can draw a Lewis electron dot structure in which each atom obeys the octet rule, then do that. The AP exam will never ask students to decide on their own when drawing a Lewis structure whether they should obey the octet rule or expand the octet in order to get better formal charges. So now sometimes you have to expand the octet because obviously 5 fluorine atoms have to fit somewhere around the central atom. But take a look at sulfur dioxide for a moment as an example. So sulfur dioxide is SO2. That's going to be 18 valence electrons to work with. You might draw a structure like this. That's a perfectly valid Lewis electron dot structure. 18 electrons, every atom has a full octet, done. You might recognize that because you could have drawn the double bond on the other side, these are 2 equivalent Lewis electron dot structures. These are resonance structures. And it turns out that the bond in sulfur dioxide is actually the same. You might also think, formal charge. What about this sulfur in the middle? This would be 6 minus 5, that's +1. This would be 6 minus 7, -1. So maybe I should draw a structure like this. So my advice to you is, don't worry on the AP exam about always trying to get better formal charges. If you can draw a Lewis structure in which each atom obeys the octet rule, then do that, unless the question specifically asks you to minimize formal charges. Then that's an option, but do not feel like you have to decide between should I obey the octet rule or not. Octet rule always works. Here's another example. This is called chlorate, ClO3-. There are a total of 26 valence electrons in the chlorate ion. The structure on the top is perfectly fine. Yes, you could do a better job of minimizing formal charges by drawing multiple bonds to chlorine, but the AP exam is not going to expect you to prefer the structure on the bottom as opposed to the structure on the top. Either one of those is fine. Unless you're given more specific information, these are both valid, but don't start thinking you have to minimize formal charges everywhere you see them. Okay, I'm now going to switch and talk about VSEPR, valence shell electron pair repulsion theory. And what this means is that you have the valence shell, which is going to be the outer electrons. You have electrons in groups of 2, so they're in pairs. And then you have repulsion. They tend to repel each other in such a way so as to be as far apart from each other in 3-dimensional space as possible. If I have 2, 3, 4, 5, and 6 electron domains, then they can spread out from each other to minimize their repulsion, and you have the following shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These are all different geometries of molecules. So for example, these molecules might be linear, or trigonal planar, or tetrahedral. I've given you some examples of molecules that have this geometry. So we have 2, 3, and 4 electron domains. Notice that I don't count a double bond or triple bond twice. This is still considered 2 electron domains. This is considered 3 electron domains. And again, I showed you these molecules before. So the phosphorus pentafluoride and the sulfur hexafluoride have the following geometries. Now, in all these examples so far, there have not been any lone pairs of electrons on the central atom. If there are, then that's going to affect your shape. So for example, this particular lone pair, the non-bonding domain on the central atom, means that the shape of the molecule is no longer linear, but bent. This pair of electrons on the central atom means that we change the shape from trigonal planar to trigonal pyramidal. And here in the water molecule, these two non-bonding pairs of electrons in the central atom make that a bent molecule. With respect to 5 and 6 electron domains, you can have all kinds of shapes. So here we have what's called seesaw. Here we have what's called T-shaped. And here we have linear. Even though we have 3 lone pairs of electrons on the central atom, the reason why this is not bent is because they all orient themselves in these positions and they separate from each other to be as far apart as possible. And then the molecule itself adopts this linear shape. So I'd like to show you some examples of these molecular shapes, and I'm going to take you now to a website. And this particular website, you can just find this on your own. You don't have to use this exact website. This is a bit.ly/PHET-molecule.shapes. You could just do an internet search on your own for PHET. There's lots of great simulations there. And I want to talk about how you could manipulate these molecules a little bit. So I'm going to go ahead and do a switch here. I am going to switch to this particular website. And as you can see, I've got 2 electron domains, and that would be linear. And I'm going to go ahead and show the bond angle. That's 180. So this would be 3 electron domains, and the bond angle is 120. This is called trigonal planar. I now have 4 electron domains. This would be tetrahedral, 109.5. I can also go from trigonal planar to pyramidal. So now I have changed from a trigonal planar where the molecule is flat. Now this is going to be no longer coplanar. The atoms are different. This is important to understand about molecular shape. So this is a different molecule. Okay, and you can also have something like the water molecule where you have 2 lone pairs of electrons. You can realize that no matter you draw this molecule, it cannot be a straight line. So again, a great website to kind of practice with some things here. I'm now going to go back to my PowerPoint, and you can play around with that particular website. Okay, so I am going to talk a little bit more about bond angles now. I'd mentioned 180 for a straight line, 120 for a trigonal planar arrangement, and 109.5. Those are the most important bond angles you should know. There's also 90 and 120, depending on the arrangement of the atoms in trigonal bipyramidal, and with octahedral, everything is 90. All right, what about the presence of the lone pair? Well, this lone pair right here is going to cause a little bit of extra repulsion on the neighboring bonding pairs. So that bond angle is going to be a little bit less than 120. Similarly, for molecules like NH3 and for H2O, the bond angle is probably closer to around 107 degrees for NH3 and around 105 degrees for H2O, because these non-bonding pairs of electrons tend to exert slightly greater repulsion on the bonding pairs. So again, knowing 109.5, 120, 180, that's great. I would caution you though, if the question asks, what is the bond angle? The answer is a number. Do not say that. If they say the bond angle, the answer is not tetrahedral. If they say, what is the bond angle? And you give an answer of trigonal planar, that is not a correct answer to this question. So make sure you pay attention to what the question is asked. If they say, what is the molecular geometry? Do not say 109.5. So if the question says, what's the molecular geometry? Tetrahedral might be your answer. If they say, what is the bond angle? 109.5 might be your answer. Now, I want to talk about something called hybridization. Hybridization has to do with a mixing or a blending of the atomic orbitals. You already know that carbon has 4 valence electrons, and they are located right here in the second energy level. Carbon has 6 electrons altogether, but there are 4 in the valence shell. So right now, would you say that these 4 electrons, in your opinion, are equivalent? Do they all have the same energy? And the answer is no, they don't. And in fact, that's what hybridization is all about. Hybridization can be thought of as a process in which these 4 orbitals, s, and then 3 p orbitals, are combined in such a way to make 4 equivalent hybrid atomic orbitals for bonding purposes. So we have 4 electrons in 4 identical orbitals, but because they were created by a process in which the 4 orbitals were combined, we have s, and then we have p, and p. The name of this orbital, well, you're not going to call it spp. It's going to be a name that sounds like it makes sense. So we're going to call this sp3. So why is it called sp3? Because 1 s and 3 p orbitals were used to make this particular hybridization for the bonding. So when you have 4 electron domains, you have sp3 hybridization. So we do count both the bonding and the non-bonding domains in this particular process. So 4 single bonds, sp3. 3 singles and a lone pair, sp3. 2 singles and 2 lone pairs, sp3. Now, in a similar way, if you have only 3 electron domains, you have what is called sp2 hybridization. So we do not count this double bond twice. That would be 1, 2, 3 electron domains, sp2. 1, 2, 3 electron domains, sp2. So sp2 hybridization, 3 electron domains. If you have only 2 electron domains, then the term we use is sp. So we do not count that triple bond or that double bond twice. That would simply be 2 electron domains coming off the central atom, sp hybridization. And now the last thing I want to mention, then we'll get to the homework, is sigma and pi bonding. So here I have a hydrogen atom, and I have another hydrogen atom. I bring them together, and now there is overlap to form a bond. So this region of space where the electron density is concentrated in between the 2 atoms is known as a sigma bond. In fact, when you draw a Lewis electron dot structure, you can consider any single bond to be a sigma bond. So here we have C2H6, and there are a total of 7 sigma bonds, and that would be sp3 hybridization for those carbon atoms. Well, what do we do in situations about double and triple bonds? Would we call this right here? Do we call that 2 sigma bonds? Well, in fact, no, there's something special for that. So let's go ahead and talk about that. We're going to talk about what happens when you have overlap in a different way. This is called a pi bond. So a pi bond is when we have electron density not necessarily in between the nuclei along the internuclear axis, but in fact above and below. Here I have 2 carbons, and they are sp2 hybridized. Now, what happened to the other p orbital, we'll talk about in just a second. So I bring them together, and that is a sigma bond. As I mentioned, what about the p orbital that was not used in the hybridization process? Because there are 3 p orbitals, but only 2 of them were used in the hybridization process. Well, the p orbitals are still there, and it is the overlap of these p orbitals in a region above and below the internuclear axis. That is what we call a pi bond, the overlap of the p orbitals on adjacent carbons. So this would be an example of 1 sigma and 1 pi bond. So a double bond represents 1 sigma bond and 1 pi bond, and a triple bond represents 1 sigma bond and 2 pi bonds. All right, let me get to my debrief and summary, and then our homework for today. All right, we talked about Lewis electron dot diagrams, resonance, formal charge, valence shell, electron pair repulsion theory, and bond hybridization. and finally, sigma and pi bonds. So here is your AP exam practice question. Because I'm a little short on time, I am not going to read these questions out to you. I'm simply going to pause. There are a total of 3 screens. This is the first one. And this is the next screen. And this is the third screen. Now, tomorrow, I will explain the answers to these questions, but these are your homework. I will remind you about the helpful chemistry resources in the video description. I want to say thank you. Again, this has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. And I want to remind you that you can go to cb.org/tech to let the College Board know if you have any specific needs for mobile tools or connectivity for taking the AP exam. Thanks for watching.